So as you all said, the atom made up of those things, right? So try to imagine going into a lab trying to figure out what the atom looks like, right? You're trying to figure out what the atom looks like, and you did this experiment. Hold on, I want to show you all the experiment. Right, where's PHP? Rutherford. Right. So there was a guy named Rutherford, and he hired two scientists. Scientists look Geiger and Martin. And I'm going to show you the experiment that he did. Experiment called gold foil experiment. All right. So, but remember, they had no idea what the atom looked like, right? So let us see online. Some of you all seeing that, right? Good. Right. You'll see now online. We'll talk about the wrong thing after. I did the right thing, right? There was some experiments that didn't really explain it properly. One was called the plug pudding. We'll look at that after. Online, you'll see that there. Rajiv, Narisa. Yeah, okay, nice. So let's take a look at the experiment, right? Okay, I'm going to explain to you what is here, right? What do you have here in cool foil? Huh? Right. What you have here is a tinted sheet of gold foil, right? Right. I'll ask the chemistry people why they use gold a little while, right? So we have a thin sheet here, Stefan, of gold foil, right? And what they took is they took something called alpha particles. Alpha is a helium. You all know what's helium? Right. So they took a helium atom, gave it a charge +2, and they shot the helium atom at this thin sheet of gold foil here. Right? So from here, alpha particle is going to go up and it's going to interact with this gold foil. That's okay? If you watch here, here's a zoom in version of the gold foil. But remember, they didn't know what the atom looked like, right? We know that these things around here shells and the little dots in the middle is nucleus. We know that, but they didn't know that. Right? So we're going to show you now what happened to the alpha particles. So I'm going to shoot some alpha particles here. Pause my first second, right? Pay attention to those purple things. You seen it? Back. What's that? Seen yellow. No, my part told you this little thing in the nucleus. Right? So we shoot in these purple, what are you can pick. Purple, purple. So we shoot in these purple particles at the gold foil. So the purple particles in that beam of light there. And we just showing a magnified version of what's happening. Tell me what you all recognize happening to the purple particles, right? Pay attention to a few of them. Nice. Three main things happening. See if you can identify the three main things that happen. Three things happening. Watching good. Some of them not happening all the time. Some happening once in a while. Watch it and take it here, and then I'll pick on some people. Then I'll pick on you, right? Right. Nice. What you all recognize happening to most of them? Just what you recognize happening to most of the purple alpha particles? Most of them, in terms of numbers, like percentage, like 90% of them doing what? Moving away. All right. And then some the others doing what? Three things happening. Some moving away, you say. What else you recognize? That's all you recognize? Aliyah? Anything? Leak, sorry, anything? Huh? Small amount of length. Hitting the nucleus and then coming back, right? Anything else? What happened to most of them? Here you go. What's them good? What happened to most of them that leave here? I'll play it again. Something happened to most of them. So some of them deflected, right? Look at this one here. Look at this one here. You're going straight. What's plenty here then? So I pick a random color here. I pick this color here. What's happening to them? You're going in a straight line, huh? So what you reckon is happening to most of them? Anybody? But there's a ratio like 90% doing it, then there's 8% doing something else, and 2% doing one thing. Anything else? What happens to most of the particles? They're being pushed away. All right, but I some of them, right? You're not seeing that most of them just going straight through. Most of them going straight through, right? Just and a small amount being what? Deflected, and every now and again you have one like that here. And hitting the nucleus and coming right back up here. Right? So you have three observations. Number one, most of them going straight through. You're seeing that? Most of the atom particles going straight through the atom. Okay, if I increase it a little bit more, right? You will see most of them going straight through. There's a small amount, like those going and those are coming close. They deflected. You're seeing that? And an even smaller amount hitting the nucleus and coming back, right? Look at it. There aren't many coming back here. You realize that was this one hits and going that way. Like seeing that? So if most of the alpha particles going straight through, you are a scientist, you are Geiger and public mass then as well. What will it come through? So if you shoot in alpha particles through a cold foil, right? And you recognize 90% of them going straight through. What you might conclude about the atom? What you might conclude? Imagine you have a ball, right? And you fell at a surface that you can't see, but most of the time the ball going straight through. What you would say pelting at? We all think, Taisha. What do you think? Yes? Yes. There's a lot of space. So the first conclusion that they came up with, is that the atom had plenty of space. And that's true. Most of the atom is empty space. Look at this here. Except for the 1 or 2 electrons on this. If this whole thing is an atom, then most of it is empty space. Right? So that was the first conclusion. What do you think is the next conclusion, Ethan? I want you to remember that those particles there, the particles that leave in here, are positively charged. Right? And look at what happens when they come close to a nucleus. Well, we know it's a nucleus, but look at what happens. Look at what happens when they come close to it. It deflecting away. What you can probably see. It appears to have something small and positive, right? That's okay. Remember, they didn't know anything. They didn't know anything about the atom. Right? So they recognized that the atom, number one, mainly had empty space. Right? Number two, they recognized it had something small. No, you gotta go in your book. Right? They also recognized that it had something small and positive. That's simple. positive, right? What happened to a few of them again? The last one, the smallest amount, the smallest amount hit the nucleus and come right back, right? What you can conclude, anybody? So there were three conclusions they make. That's one. Think about it. A real small amount hitting something and coming right back at it. You had a guess. Gabby, what do you think? What do you think those scientists, Geiger and Marsden, would have concluded? They were two German scientists, right? And they did it in a guy's lab named Rutherford. Okay? So sometimes you will see Rutherford experiment, sometimes you will see Geiger and Marsden experiment. They both mean the same thing, right? Yeah. Shelby, what do you think? Anybody want to guess? Ethan? Look at. Yeah. And Ethan, I want to guess. Randy, no guess. So think about this. If a particle, so they recognize that a real small amount of particles left and come right back at them. What it probably meant is that the middle, which we call the nucleus, was small and solid. So it hit something solid and came back at it. So the third conclusion was that it had something small and dense. Right? So it had something small and dense. So those were the three conclusions of the Geiger-Marsden experiment, which we know about. Right? Empty space, because the atom may be empty. We have a small positive core, which we later call the nucleus, and that same core was small and dense. What gives the atom all its mass? The nucleus or the shells? Nucleus. So it means that whatever in the nucleus was solid. That's okay? So okay with that? Did this experiment indicate anything about electrons? No. Nothing really about electrons. Right? There's a next guy named Chadwick who did that later on. But I'll be your homework. Chadwick. Alright? You're okay with that? So if you look at the diagram I sent in the group, right? Look at the first diagram I sent in the group there. Huh? What shows up
We don't
Right. Look at that diagram there. Right? Watch it there. Watch the diagram. So if you look at the diagram online, I sent it in the group, right? Look at the diagram. It have the alpha emitter, it have the gold foil, and the detecting screen around it. You see it now? So the detecting screen is where the alpha particles hit, and they were able to come up with the conclusions and so on. Okay with that? Right? So the little detecting screen around it that you see in that image, right? The detecting screen, every time an electron hits it, right? You're able to see, okay, electron hits in here and hits in here. So they recognize that most of the electrons hit the opposite side. They recognize a few were deflected all the parts, and a small amount came right back at him. So you can see how this screen will work. Earlier, you can see how the screen will work. It's circular screen there. You can see how that will work, right? All right. All right. So that was the model of the atom that we studied today, right? And we will focus on that. But I want to show you all something that our next guy did. His name is Thompson. Right? Watch what Thompson did. Changing Thompson. Tell me what you all think about his model. Right. Watch this here. So now the next guy, before this experiment, he thought the atom looked like that. He thought it looked like a plum pudding pie. Right? So here's what he thought happened, right? Right. So let me explain his model first. Right. Let me explain his model first. He thought the atom, of course we know it wrong. Right? They had plum pudding pies long time. It's like a pie with plums in it. Right? And he thought that that's what the atom looked like. He thought that the atom looked like a big pie with plums in it. And the plums were electrons. Right? And this big cloud here is kind of what we call the nucleus. So he thought the electrons were just floating around in this big cloud. Right? So what this simulation is showing you here is that if this was right, then this would have happened to the other particles when it goes to the food. Nothing would happen. Right? So really and truly, those guys, Geiger and Martin, went in expecting that to happen. Right? But did that happen? No. Things were deflected and things came back. So they had to reshape the way they were thinking about the model of the atom. Okay? So in multiple choice, they might ask you about J.J. Thomson's plum pudding. This is what it is. Right? A sea of electrons inside what they thought was a nucleus. That's okay? All right. So this is what they thought the atom looked like. Online, you're okay with that? Right? But of course, this here is what we know the atom to be like. And this is a nice simulation because you all don't draw it like this. When you all draw your shell, you draw them equally spaced, right? But you'll recognize that your first shell is here. As you go further out, all the shells kind of close together, right? But the atom doesn't really look like this in real life. What does it look like? What does it look like? No, like the shells. How the shells is look? Like the way the planet orbit, it looks like that. Right? But this is easy for you to understand for now at least. All right, nice. So let's put the handouts. Right. Let's take a look at this one. Oh, by the way, your hook here, right? The left hand corner there. That's your hook. And you know what? I think when this all can happen with it. For the figure, it's 2 months. So I just tell you, okay, with this stuff with it. Idiot. Huh? All right, so you okay for your side? Yeah, you okay for your everybody clear. All right, so what's that fast then? I want you to just take a look at these guys, right? Thompson, well, we just did Rutherford, Bourne, Chadwick. I want you to take a look at what they came up with. Right, so that's the name. If you see TM experiment, same thing. Right, so this experiment have 3 names. Geiger Marsden experiment, Gould foil experiment, and Rutherford experiment. You can go by any of those names. All right. So the Geiger Marsden experiment. So the Geiger Marsden experiment established the nucleus structure of the atom that currently studied. The apparatus was set up as shown below. Right, look at here, right? This is what I was showing you a while ago. This here is a detecting screen. These are red lines are the alpha particles, and it shows you that the alpha particles went all around it. Okay, nice. And you have to be able to label this. Which one here it goes call again? Which one? That one. This one here? Right. Nice. Alpha particles were incident on a sheet of gold foil, and the behavior of the alpha particles was noted. Remember that the alpha particles are positively charged helium ions, right? They observe the following. So if a question asks you what they observe, these are the things that they observe. Most of the alpha particles were undeflected. Some were deflected by small angles, about 7%, and a few were surprisingly reflected and bounced. Right? What did they expect again, Chris? Yes, pass straight through, right? But this happened. Okay? And Tishish, based on this here, what were the three conclusions again? What were the three conclusions? Huh? Yes. After the experiment, sir, it had three conclusions. Huh? Those were the observations. Those are the three things they observed. I want the conclusion. Most of them went straight through, which means that one. We just do it about 2 minutes ago. They can minus, they got the double minus that. Yeah. Yeah, that's one quick. Yeah, what did you conclusions? No, you could. Aaron. Aaron doesn't help me out now. What were the three conclusions? That will be the little things I wrote in red. Most went straight through means that the atom had empty space, right? A small amount was deflected means that the atom had a small positive core. And the third thing was it appears to be small and dense. Okay? Right? Appreciate you, remember that? Right? So here's the next way to draw it. If they ask you to draw it, you could just draw the diagram, right? The little orange things there are the gold foil atoms, and the yellow lines are the alpha particles. Right? So their conclusions were, since most of the alpha particles passed straight through, then the atom was mostly made up of empty space. From the alpha particles that were deflected slightly, gave an idea that the atom center or core was being positively charged. Since the positively charged atom was repelled by a small angle, please remember that light charge is repelled. Are you clear with that? Yeah, exactly. The few particles that were reflected appeared to have some sort of head-on collision, resulted in a conclusion that the atom core was smaller than that. All right, that's plenty worth it done, but all I want you to remember is empty space, positively charged core. Underline it here, right? Empty space, a certain core that's positive and smaller dense. Okay, those are the three conclusions. All right, and as a result of those conclusions, right? I know you have a thing, but write down this one. Write down the observations and the conclusion. Just one line. One line, right? But some of them might never open their hand up like. And they got like that all the time. Okay. All I want you to write is the three observations in your own words and the conclusion, as short as possible. Write the observations and then those conclusions highlighted there. Let's do that. So I write everything and otherwise write a small version, right? So observations will be 90% went straight through. 7% were deflected and 3% were reflected. That's all I wanted to tell. And then parallel line, conclusion, empty space, 4 positive, small and then. All right, let's go. All right, let's go. Next part here. Right, well, come on, did you do this? Put on your camera. Yeah. Okay. I told the atom I can go on to 1 right, same thing. Same thing, right? So from the Geiger Mason experiment, the atom that we studied today looks like that. Right, Shishish? Nucleus in the middle, shells around it, right? So we're gonna take a look at the structure of the atom, right? All this they might know already from Form 1 or 2 or something, right? So the atom was discussed before with the aid of a few more experiments, contains two main components, nucleus and shells. Nucleus is here. The nucleus has the protons and neutrons, and the shells, the little circle around it with the electrons. That's okay? Remember that? That one? Yeah, remember this? Right? Nucleus with protons and neutrons, and the shells with electrons, right? Right, something small to remember here again. Right, the following table gives some information about the particles. They gave you the relative mass. What this means here, what the relative mass means, it means that when you compare the masses to each other, right, it shows you how much bigger the proton and neutron are compared to the electron, right? So the largest is which one? Ideally, the largest is the neutron. But at our level, we say that the neutron and the proton is the same. Right? They carry a mass of what? Right? They carry a mass of 1, and because the electron is so small, it has a mass of 0. You okay with that? Okay with that, right? Yeah? Ishish? Remember that? So these are the values that you will use. Proton, positive charge, neutron, 0, electron, -1. Where are they found? Proton in the nucleus, neutron in the nucleus, electron in the shells. Okay with that? Right? But same thing I was now talking to you about, right? They have the same mass and so on, right? Right. The only thing that's a little bit different in physics is this. In physics, we call protons and neutrons nucleons, right? We use the word nucleons. The protons and neutrons are called nucleons. Anybody remember what you get when you add up protons and neutrons? What you get? The mass number, yeah. So in physics, they might say what is the nucleon number. Okay with that? So mass number means the same as your nucleon number. All right? All right, the next part I want to do on code. Right? You may or may not remember this stuff, but I'm going to go over this quick, right? This is how to count code. All right. So we need to remember that they're going to give you a symbol, right? And then they're going to give you something here, and at times you will get something here. Okay? A is the what? A is what we call the mass or the nucleon number. Right? C is your atomic number. And C is the charge. Right? But everything in the periodic table has a charge of what? 0, right? So for now, we will give it a charge of 0. Right? I want you to remember that your mass or nucleon number is the protons plus the neutron. Your atomic number is your protons. And because the charge is 0, what's the same? What's the same? And it's done. If the charge is 0, what two things are the same? The neutrons have no charge. The protons and the electrons. Okay? That's something to just to remember, right? So if I gave you an example like this, let's say I gave you let us do something small. Let's say helium. Helium coupled up city, right? Let's say I gave you something like that. Right? And I asked you to draw that. Here's what you need first. You need protons, which is 2. How much neutrons in here? It'll be 4 minus 2. And how many electrons? 2 as well, right? Because these two are always equal. Okay? How do we draw this? Sorry. How do we draw this? Right? We start with a nucleus. In physics, you have to tell them what the nucleus has in it. Right? So you're telling them nucleus with two protons and two electrons. Sorry, two neutrons. Okay? You okay with that? Right? So a nucleus has two protons, two neutrons. And then there are shells. In this case, the shell has two electrons. Right? Anybody remember how to break up the shells? How do shells work? Like how many electrons before initially? So shells hold two electrons and then eight, and then well at your level, so on, eight and so on, right? Right, but it's more. I think it's 2, 8, 18, and so on. At your level, it's 2, 8, 8, 8. That's okay? So the first will hold 2 and the rest will hold 8. Are you okay with that? Yeah. So I will try one for me. Try sodium for me. Try that for me. Remember, the first shell can hold 2, second shell can hold how much fishes? And the next shell can hold, well, at this level, right? Try that first. Now you have. You can give it a now. But first class word, yeah, but Friday word. Anybody? Come on, come on, try. Come on, try. Go to watch mark. Yeah, yeah. I'm good. My first TikTok. Huh? My first TikTok. Wait, let me change it right there. That's why. Right, so we're trying to draw here the atom for sodium, right? Model. Take too long there. That's not out of code. Right. Do slide two. Do slide two. Focus. Don't write down, let's put in numbers and enjoy it. Let's put in numbers and enjoy it. Right, so neutron 12. What I get up? 12 neutrons. Right, how much protons and electrons? 11, and how much electrons? If charge is correct, proton is correct. So electrons. Nice. And then break it up to like two. Yeah. How much? So that's my part. I enjoyed 2 shells one time. Somebody missing anything, right? Somebody missing anything from the diagram. That we do. Yeah. Yeah, yeah. Yeah, yeah, yeah. Yeah, you want to watch. Yeah. You okay with that? So that's the model of the atom. All right. Next thing that we're gonna do, today we're gonna take a look at what happens when these particles do that. They do it in the form of radiation. All right. Right. Log back in here. Yeah, log back in, everybody. Yeah, online, everybody log back in. Log in quick. This is what we did just now. Wait, what the volume? Right, login quick. Online employee login. The nicest little track of them online to I'm still waiting on some people from online. Richie didn't join yet. But Jalen and Celine and I on this. Login again. Login quick. Right, everybody in, right? Both Ethan, gotta get through. Which one is it? The one with Ethan, Chi, that's it. Right, no copy now, yeah? I watch you post now for next year. If two only have the same score, one goes now to jump off. Alright, go. What's going on with this for you? Alright, no volume. I don't know. Just do it. Just do it. Oh, this is something. Let's go. Let's see. Right. Yeah. Next one. Keep your scores, right? Well, how are we keeping the scores now? We tell it up here. So you can see who's in top balance. What it was some. Aaron slept. Oh, slept one thing. Ali working on my senior. Anyway, at least all again in the right. That's a good sign, right? Just get memory faster answer, the more points you'll get, right? So read it here and figure out your answer. I will get this wrong again. More than one answer here. More than one answer here. Double points. It tells you how many answers you're looking for. So you use that one. One keyword together or divided by two. It has three answers, huh? Right? Don't click two alone. You have to click all three. Amen. Nobody get that one wrong. That was good. 17. Somebody should get the click. The red and the green. Bandina take over with close one. That's good. Nice. I can see how Kahuda does so. Spell properly, please. Spell it wrong again, wrong. Wait, I hope I spell it correct. No capital, all lowercase. What? All lowercase. Which one? Yes. Yeah, just spell it all lowercase. I don't know if they'll give it up. Sometimes it's case sensitive. Sorry guys, still will be capital, eh? Shabby, can you put capital, eh? And you still get? Alright, nice. Actually, Shabby is important over it. Tell you who na bhai, tell you who na. Tell you who na. Did I get this wrong? That's nice. Yeah. 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 So this Friday, we have some like right? Yeah, let's not know. Yeah, what is comfortable? Yeah. What is comfortable? Yeah, to go for the Who in that? Well done, standing up. Who gave second answer? Second answer? Jabi comes or Jabi comes second answer. Nice. Okay, well done, Olin. Right, so keep the score because I'm going to add on to this as usual, right? Next week, add on to it and so on. Alright? So next week we'll continue from right here. I'll press them to tell you if I add only half an hour for next week. Alright? We'll see you this time. We're going to see how I survive this all night. And we'll see how it goes. Go, sorry, man. Master's next.